or become an advisor somewhere. But luckily, with my students, with my colleagues, and also with this new university that we set up, I was able to be relevant and eventually maybe even ride a wave a little bit, maybe think a little bit further on new topics. So here I'm here to report back to you, what has happened, and also some of the vision, that I want to share in terms of path forward. Okay, so I'm not going to talk only about large language models. In fact, majority of the time will be devoted to what's beyond that, because we all know LLM has been already, a known fact of success, right? What's next? All right. The mouse has been moved, so. Yeah, okay. Right, so let me begin with a quick report about my 4-year adventure outside of CMU. This is a university we built in Abu Dhabi of United Arab Emirates for the past 4 years. And we started from ground zero with almost no professors, no students, and very, very few staff. And now, we are about to celebrate the 5th year anniversary. And if you look at the CS ranking, which we always go for a more objective, metric-based ranking, I believe we are around, 11 to 15, depending on which particular day you look at that. But of course, we don't overplay the trick just by zooming into a tiny department. We basically covered all the areas already served in the university. We're now at the 11th, and we're the first in MENA. And this is a growth. It's actually one of the reasons why I want to go there and do this project. As a department chair, as a dean, as a president, your dream is to have an infinite headcount and budget to grow. I don't have infinite, but we managed to grow very rapidly in the past 5 years at a rate of 50% at least growth in faculty number, in student number, in researchers. And also we put a very high emphasis on quality. You can see 40% of faculty come from the top schools worldwide. And 25% of the students also come from top schools worldwide. And also it's very diverse. Amazingly, among our 300 to 400 students, 49 nations were represented. This is kind of a amazing experience, seeing all these international students coming together to study. And academically, here are the programs we have so far. We started from 3 departments: machine learning, NLP, and computer vision. I draw a lot of inspirations and experiences from what is happening here at Carnegie Mellon, and kind of beginning by reproducing whatever is here. So we started from these 3 departments, and then we add robotics and computer science. And this year we are adding HCI and the statistics and data science, and also computational biology and computational medicine. And also at the same time, we built horizontal, centers, on topic-specific problems. And we have a few new schools in the coming years. Here is a summary of the achievements, and I'm going to then wrap up about the bragging. We are now well-ranked, both in AI, but also we are going to be covering all the CS disciplines. And right now we are 80. And we have over 1,000 papers in those top conferences: NeurIPS, ICML, ACL, CVPR, and so forth. And we have already graduated 3 classes of graduate students. They number to 200-ish. And most of them stayed in the region, to become part of the local economy. And also we are generating community impact by focusing on very interesting and relevant projects, in particular in the space of generative AI, and the AI for digital healthcare, and also AI for sustainability, which are obviously the important topics in that part of the world. And here is the path. Okay, so we are just finishing these first 5 years. In the next 5 years, we are adding 2 new schools: digital public health and decision science. And here are the layout of the departments that we want to build. We didn't start from art and sciences and engineering schools, because there is no advantage for us to start that way. There are many schools who are doing very well on that. We really will be trailing, from day one. We want to be leading from day one. Therefore, we set up, a reverse direction, starting from the new areas and less competitive areas, so to speak, and then eventually covering all the other areas with the support from AI foundations and other things. And in steady state, which of course will be way after I step down, we hope to see a university that is, having a few hundred professors, few thousand students, and be a pillar, be a Carnegie Mellon, in the Middle East. Okay, so now back to our topic for today. I think it's probably interesting to begin with this debate about what is AI and AGI. Everybody's talking about that these days. I've been asked by many people, not just the researchers, but also politicians and entrepreneurs, decision makers about that. And here is one version of the answer. You all know Sam Altman are very bullish. He's very bullish about his, GPTs, right? And he laid out this roadmap of 5 levels, starting from chatbots, which is now, and then into reasoners and the human level problem solving, which is about to happen, maybe already happening, and then agents and scientists and then organizations. That's basically his vision about AGI. He really believes that the GPT is going to deliver you artificial general intelligence. And obviously, we also know on the other side, people like Yang LeCun don't believe that, right? So they say the current system is not even as smart as a cat. And therefore, that's a wrong path toward AGI. And then there are people, like Andrea Capacci, who will say, it's like more like a jacked intelligence. Sometimes they're amazing, sometimes they are dumb, right? So that's basically, I think, that covers current spectrum of the debates in AI. When I was approached with similar problem, I actually don't feel comfortable even in answering, AGI or AI, because that intelligence itself is a EU-defined term that we unfortunately inherited, as the name of our field. But intelligence itself is a very subjective thing. Some people who appear to be very dumb to you may be very smart to me, like a musician who may be terribly dumb, in social life, but could be a genius in performance, right? So we have that kind of experiences. And the Turing test itself isn't solving the problem because it's really about putting something behind the curtain and you tell whether he's a human or not. It's not about how much problem he can solve for you. Right? I think that there is some alternative way of maybe defining, intelligence in terms of a capability, right? And maybe utility. And also even go beyond just the lingual intelligence and communication. You can communicate in many other ways. In fact, we communicate way beyond just speaking to each other. So that hopefully sets a different stage, than what current AI debate is about. And I want to start by putting some, maybe concrete statements about utility and the functions. Just like, with human needs, our entire kind of path of life are defined by our needs, right? So this is the Maslow's pyramid of the human needs. When you interview, an employee, or when you go to look for a boss, I'm sure you ask, a question like competence and capabilities and so forth. And you actually also have your own tier about the level of difficulties or the values of competences. And here is my pyramid, right? We started from you need to be literate, be able to read and listen, you need to watch. And then you can reverse that and by writing and speak and draw, right? And then on top of that, you do some logical reasoning, you can plan, you can execute, you interact with others, and logistics and tactics, strategy, maybe you become a prophet and predict the future, right? And you can even, put some, benchmark tests, over these capabilities. That defines basically our matrix of measuring, a particular functionality. Is intelligence part of that? Well, it's a adjunctive. You can say that intelligent, but you can completely ignore that word and still go with all these functions. It's just like an aircraft carry you from A to B, you call it flying, but it's flying in a different sense than the bird flying, right? So that word itself isn't very important. So that's how I feel, comfortable, to study, building systems that is intelligent, so to speak, measured by functions. And for the top, the bottom two tiers, I think we all know that the GPT is now, excel, in that space, doing very well. On top of that, I don't know, maybe a Chris Boy is doing that, but we probably don't need that immediately. And then what's in the middle? I think that's basically what the open question about AI going forward is, right? It requires some additional models, right? So model again is a man-made entity, and it is subject to design. And we all know this very famous quote from George Cox that there are no right model, but they are very useful models. And the GPT is one of these useful models. Is it the right model? You can start asking questions like that. I would say depends. If we are talking about the model producing the next word, I think it's about right. I don't imagine that there will be other systems which can be doing better in the reasonable future, and just in predicting next word, better than GPT. Whether I understand the next word, whether I can, maybe tell you additional insights about next word, that's a separate question. But my goal is to do next word. Then GPT is doing very well. And yeah, so but the question people always want to debate, especially among the academia, is about whether LLMs, really understand, or it is doing string manipulation. I bet you have your answers. Maybe you agree that it is doing string manipulation, but maybe some ultimately believe it is understanding. It doesn't matter. There are different answers. And you can even ask a more kind of a profound question. Does the LM have an internal word model that I understand not only those words being predicted, but also the context, the background, and so forth? So these are the questions. And obviously, Yang LeCun is very pessimistic. And he, based on his own experiences in this whole field, he concluded that the large language model has no idea about the underlying reality of the language it describes. Okay, and he has his reason to say so. But the Ilya actually has a very different opinion. Without the proof, he actually would speculate that because this model is doing so well, in making the next word prediction in content generation, something must be learned already, other than just the surface connectivity association between words. There may be some later representations that it is still, from training. It's just like no one is looking at it. And in fact, it's not even lookable because the trace and the internal intermediate data are not even published. Therefore, there isn't a community around to study it. And you can also ask the same question to video models, right? Sora, for example, produces amazing videos. And you can also ask, just like in language model, does the video generator really understand what it's generating, right? And or it's just manipulating pixels. My answer is that I believe it is manipulating pixels because I have evidence showing that the model doesn't understand what it's generating. And I will show you why I say that. But the point is that, does it really matter or not? Right. When you ask a language model, or when you ask a microscope, that you look at the microscope and something, all you need is a magnification of the image. You don't ask them to explain to you the law of biology, right? You explain that. And that's my attitude toward language models and video models. If all I need is the generation of the content, then I got what I got already. And the next thing isn't really what the model was made for in the first place. So that basically leads to the following sort of questions, which probably will be useful for we computer scientists as a guiding light for building our systems. It's focusing on capability, efficiency, maybe also the right representation. For example, you can ask if a text and pixel space is even the right space to answer my question, right? And that's actually a very interesting problem because we human beings doing our reasoning not always in language. Right. For example, when I drive, when I see some object coming to me, I don't turn that object into a language in my brain and then do my word connection. I'm going to directly respond to that in some other ways. Right. So that hopefully gives some insight about how model can be built which starts the rest of the talk. Let's start from what we want from this model. And as of now, we want, for example, generating text content, say having a bot, writing emails for me and clean up junks in my box and so forth. I think the LM is going to be maybe already very good at doing that. I know many of my friends, including, I can tell you, senior ministers in the government, who will be using ChatGPT to draft a speech and then spend a few minutes and polishing it and give wonderful, wonderful talks. And that's actually a real utility right now. People really appreciate. I heard people saying that lawyers, accountants, maybe even doctors will be gone because most of their work is to produce a large amount of text that is not even meant for you to read. It is meant for the other robot to read. Therefore, both sides can use robot to generate. So that's possible. Then what's our next need? Our next need may be letting a bot to drive a car for me, letting a bot to book a trip for me, or maybe I want to start designing medicine, drugs, and so forth. Each of them is a very specific function. Okay, it is not asking you need to understand all these nuances and cognitive science and the biology behind it. I only want the functional. And if you buy in that kind of mindset, then what about we just focus just that? Simulating, for example, just like what the LM did in the lingual world, simulating a physical world, simulating a social world, simulating a biological world. In a sense, the model is a simulator. What you see from large language model is the outcome of a simulation of your linguistic activities. And that extrapolation can go to other modalities. And that's basically where I see maybe the future trend is going. We may need models going beyond LM in the form of, for example, an agent model that can make use of language model as a component to do the lingual inference part, but also other model like a word model to do the spatial inferences and other inferences. Maybe we need a biological model, which I'm going to talk about next week, to understand DNA, RNA, protein structure, gene regulation, cell, and so forth, and then answer the questions listed above in a holistic fashion. And but on the other hand, does this model really know the logic of a biological regulation and so forth? Well, if it does, that's good for it. But if not, if the answer of the queries are correct, maybe it's also okay. All right, so just last but least, wrap up this opening. The university that I'm helping making is really aspiring to take a lead in all these research topics. That's why it's called the University of AI, even though it is going beyond AI in the future years. We've been working very hard to produce all sorts of foundation models, thanks to a larger than usual computer infrastructure than a typical university can afford. And we are trying to also serve the community by providing platforms like the Chatbot Arena. Many of you probably are familiar with this platform where models get ranked. And also LM60, which I'm going to talk about, to offer additional insight and information to study LLMs. Okay, so large language models. So the way I understand large language model is that it is no more, no less than a model that simulates the linguistic or lingual activities and communications through the next word prediction. Basically, it's a very, very bizarre but useful kind of definition of the work. Basic definition is that anything that you want to frame and define and evaluate in the space of a text can be delivered as a next word prediction. Okay, that's basically what the large language model's basic assumption is. Be it a math reasoning, logistic reasoning, encyclopedia QA, medical law bar, everything, as long as it is in text, I'm going to recast it as a next word prediction. But I do it so well that for any possible kind of prompt of the word, I give you what a human being would give you back in terms of text returns. And that's why, the modern way of training large language model is to use as much text as possible ever created from human civilization, right? And they put aside debate about whether it is AL, HN, not. Basic function tells the whole thing. And as of now, I think the landscape of LM has been pretty much settled into two quarters or two sectors. One is what I call I don't want to call it the closed source. I want to use a more positive word. It's open API models. You can all use it, pay or free. Yeah, these are the private sector, models by Gemini, OpenAI, Google, and Anthropic, and so forth. So open API. The second section, well, it's called open source, but the truth is it is open weights, right? You didn't see the source, did you? I didn't, right? But the weights are there. Sometimes the data are there, and you are free to download these weights and fine tune, for the downstream tasks, which is very useful. And that's actually also why, now Meta is very, very bullish, in this whole venture. I want to cast their value and their vision on top of it. But still, as an academic, I have to say that I feel I'm irrelevant because I cannot really reproduce the results there, right? I don't have a machine, I don't have the code, I don't have anything. All I can do is to be a parasite on top of it and doing the fine tuning and become their agent or client. So in that, spirit, we are trying to represent the academic better with our resource in the university and open up a third section, which is what I call 360 open, because the open is already used in there. I put a 360 really means open source. Okay, the open source means that you open the code, you open the data, you open the checkpoints, you open the training log, you open everything. Okay, become transparent, and then let the community, to study and use. And also the license, obviously, is almost like a vacuous because you can do anything with that. In here, in fact, there's a strict license restriction. You are not supposed to run it in a certain way on a certain cluster and so forth. In here, we try to be a little bit more flexible. And on the other hand, we are a small university. And in fact, we also have some partners with students in CMU, in Stanford, in a few schools. But we are not a billion or trillion-dollar company. Therefore, the resource is still limited. So we are not as performant as those other models, in our earlier release, but we are picking up. The latest model K2, which was roughly positioned against Llama 2, was actually successful in outperforming Llama 2. But of course, when we outperform Llama 2, Llama 3 was published already. So we are always training behind. We have a few next steps. For example, we are now in the process of training a K2 plus 70 billion, which hopefully will be better than Llama 3. And we are preparing to train, a 1 trillion parameter mix of experts, K2, MOE, hopefully to be on par with a GPT-4. That will happen hopefully next year. So let me say a few words about this project in detail, right? It's about really sharing everything. And that's basically just an example about what we are trying to share and also what we are trying to achieve. We want to really, first of all, demystify LM so that the people know what's happening during the training. You probably don't appreciate how difficult and how painful it is to train a model. Okay, you are sitting on top of a few thousand GPUs, maybe a few hundred GPUs, and you have overheating on the nodes now and then almost every day. You have nodes dropping off the grid every day. In fact, you have mistakes all the time just by a particular troublesome data points, all that. And then what you do? Okay. And it's not about you start a machine, you stop and restart because every restart costs you tens of thousands of dollars, if not more. And you have to basically be smarter in throwing away back, corrupted data, in keeping checkpoints, start from the middle. All this empirical practice was not often reported. So we're going to report that and also invite people to come up with better solutions. The data also we prepared for other people who care to reproduce the results. And there are a lot of other things I'm going to show later. And the K2 is so far the most performant, truly open source, large language model. It is a 65 billion parameter English large language model. it is trained with a special kind of emphasis on mathematical reasoning and logical reasoning. And that's how the training strategy was designed. It started from 1.4 trillion token generic data with everything. Okay, math, legal, medicine, coding, everything. And then in the later stage, we have roughly 100 billion token, heavily weighted on mathematics and the coding, because our patronage of the project had a particular interest in the mathematical reasoning and IQ. Therefore, we have to make him very, very satisfied to continue the support. And the strategy seems to be rewarding. That's a scorecard in comparison with the then state-of-the-art models, namely Llama 2, and then there's a Forecon model and a few others. So we are doing okay, either number 1, number 2, in that league. Even compared to Llama 3, which come later and bigger than us, we're not behind by too much. But of course, if you just put the bigger picture together, we're still very far away from the SOTA models. For example, this one is, I don't know, I think at least 20 times bigger than our models, if not even bigger. So I'm not surprised with the performance gap. But the more important thing is that we become an academic team that is in the game. Okay, now students and professors can actually have a chance to take a closer look of these monster models and hopefully figure out what's going on out there. There are some particular dimensions we do very well because there is a predefined goals. For example, in terms of IQ, which our sponsor become very, very obsessed, passionate about. We do a very, very diligent sequence of fine-tuning, instructive tuning, and so forth. And you can see that it's rewarding very nicely. We are on par with some of the best of the league, in the space, even though our model is less than a tenth of their size. You can see here it's on the mathematical reasoning. Yeah, still there are some very good ones, but our model, being a 64 billion problem model, is doing remarkably decent in the competition. Now this is the crown jewel of the whole project. These artifacts are all out there for people to download and play with, which contain, for example, a few hundred intermediate checkpoints. That means it's not released in the form of one model. Okay, in the sense 120 models are released. Every checkpoint is a full model. You can see the model basically grow across time, just like a baby, training across the days. And then different prompts and outputs, different metric curves, evaluations, and so on and so forth. Right. Our K2 Plus, which is now under training, are using a 12 trillion token data set, which is roughly 10 times bigger, and it will take a lot more time to get ready. But yeah, we are trying to really promote this LL360 to be the academic answer to those big corporates, to create a healthy balance in purely profit-driven industrial production versus curiosity-driven academic investigations. And these data actually are quite interesting. It's very underused. My team, my colleagues in MBZUI, even here, just do not have the energy and time to just fully leverage on that. For example, given all these traits, you can actually start to visualize, when memorization of certain concepts, certain tokens take place just by plotting them. And we don't have enough, energy and time to even plot all this information yet. You can also start, investigating neural behaviors. For example, you fire a particular, say, prompt, and you can actually start to visualize what happened inside the model. How different neurons gets fired up and the information gets propagated. So all this can be very interesting, both for cognitive study and for algorithmic study. And of course, you can do interesting experiments like, injecting, synonyms and other, carefully designed psychological and physiological experiments to prompt the machine and the system in different ways. Yeah, so I invite, basically the community to take a look at this data set and maybe even contribute yourself, if you have similar models. Now, what's left in LMs? I think it's a very mature field already. The architecture is stable, and but there are some rooms to go further. And this is my own, checklist of to do, that can keep our group busy. On the first topic, priority is to how to make the system even faster and cheaper. I was in one of the Docker-sponsored workshop about the future of LM. One remark really struck me. With human brain, when we do reasoning, how much energy we use? A few watts. Here we're talking about a few gigawatts. Why is that expensive? Right. So there's a lot of room without losing performance to reduce the energy. I think that's a topic you can do in many different ways. Using both algorithmic approach and a system approach and other co-design approaches. So that's a topic that we've been working on. I saw your raise already. Let me finish this page and done. Data, not all data are equally good. How do you weight the data, and how do you actually qualify, data points and so forth. I have my own mixed feeling about that. I know there are a lot of research on data. Then I invite them, hey, you have a good algorithm. How about you use it for my 1.4 trillion tokens? Okay, they all step back. So yeah, I think to really have an impact, in this large LLM model space, you have to be serious about the size. Your algorithm cannot work on one machine and with a few terabytes of data. That's not enough. You have to basically go that big. And then if reading the data is already so costly, before you apply any algorithm, then forget it. You have to be smarter on that. Tools is another space. Right now, I think that the tooling space for inference and learning and continuous learning is chaotic. You get a lot of different diversities and all that. So there's a space to do some systematic work. Scaling law still needs to be understood better, in new modalities like visual and audio and so forth. And then integrating LM is what I see to be the most important future, because that model can be actually a building block for the more advanced models that I'm going to talk about today. You have a question there?
Yeah, so great job with the K2, but I'm just trying to understand, does K2 also have the RLHS component?
The K2 has what?
Reinforcement learning, human feedback component, or is it just the next to prediction?
Your reinforcement learning, your additional prompting is a post pre-trained exercise. Yeah. So K2 is a pre-trained base model. You of course can use that, to open up, the downstream tuning tasks.
That's pretty impressive if it's doing that performance even without reinforcement learning. Right?
Oh, for the mass learning, of course, we're doing reinforcement learning for prompting and also for experience. Yeah, it's in fact that's true for every model. If after you post pre-train it, if you want to put it as a chatbot or as something, you have to do all these things anyway. It's just about how much good data you have to really squeeze out that any performance gains.
What was the other thing you said? There was something engineering when you did the math thing. What was that?
Oh, in the math, you want to have a very, very good, the problem examples, and it's kind of supervisor. You can have that the reasoning kind of the templates to the fine-tuning. The base model itself does not, do very well without such fine-tuning exercise. Yeah, so I think now the whole playground in LM is become very clear. You start with a general purpose based training or pre-training for the large model, and then you do task-specific fine-tuning and prompting depending on your own, data and also your own tasks. And I think what's out there for example, Llama is to make the first step done for you already and release the weight for it and you do the next step. But the very few people are in the space of the first step, how to do the pre-training and the base model building is not clear. So I don't mean to go to the details in here. So we have some projects working on algorithmic and the system innovation for LLMs. You may have heard about something like the tensor parallelism, Kaplan parallelism, page attention, and VLM and so forth. So this work actually comes from some of the projects originating from here. And recently, there are efforts on federated machine learning, mix of experts models, in the true distributed sense. We also have some research on that. And recently, you all use LoRa, for example, for your fine tuning, right? So that's another kind of way of reducing the cost, through low rank, through quantization, through compression. Yeah, so these are, the current active technical topics the field has been working on. So we have some results there as well, but I'm going to skip that for the sake of time. And the LM Foundry. There is also room to make some impact in there. Right now, there is a very, very diverse code base people use to do developments. You go for Megatron deep speed for parallelization, right? And then you go for maybe weight and balance, for logging. And then you fine tune, using the Hugging Face, tools and so forth, right? You need to basically maintain multiple accounts and log here and there. And sometimes those interfaces don't talk to each other. There are a lot of headaches in maintaining, a continuous data logs and the repository and so forth. So in our group, we happen to be having technical contributions and the work activities in the past in all such. So we managed to put all them together, and there is a chance that you can see, a one-stop place, for such a foundry down the road. I haven't done that, but there is a potential to do that. Okay, so now I'm finally getting out of LM, which I didn't mean to even say too much. I think that the more exciting thing is to ask what's next. So LM, to put it in a nutshell, is about simulating lingual and communication node activities. You can just use the same kind of a strategy to push a bit further. How about we simulate cognitive and behavioral activities and other outcomes? And you may ask, yeah, maybe LM is already doing that. Let's see a few examples. It turns out that LM indeed, sometimes make funny mistakes and expose terrible weakness. And here I have a summarization of 3 points of weakness. Even in lingual reasoning, here is an example. If you read this text, in fact, you may do this now with 4.0, you may still get the answer wrong. Okay, you probably also know the very famous capacity example about the 4.9 and 4.11, which one is bigger, right? And but this one is a little more tricky because that one was fixed the next day when the question was posed. This one still hasn't been fixed yet. So the text says that there's a plan to survey the mental health of undergraduates. And I'm going to do the following. I'm going to ask the freshmen this year, next year, the sophomore, the third year, the junior, and the senior. What's wrong with this plan? I asked you. So GPT, here's the answer from 4.0. Okay. Basically, it says that it is something wrong. It doesn't track the same group. Yeah, surfacely, it didn't track. It tracks it gets the freshman now and then the sophomore, then they look to be the different groups. But they ignore the fact that it's the same group. This year is freshman, next year is sophomore. So there are background knowledges that GPT-4 is not able to capture. Another limitation, embodied reasoning. We all talk about robotics, right? And to have a robotic mate in your home, they need to, be able to, for example, navigate, but also moving things around and also sense a lot of things. And that's not a forte of LMs. And here I get one example. For example, just do some block moving, move your furnitures. You enter this into the GPT, you are likely to get an answer like this. They will give you a few steps. Okay. It is a typical mistake by autoregressive reasoning. You look at the answer first and you backtrack, right? Okay, there is a orange one on the blue. I'm going to pick up the orange one and put it on the blue. And then there is a yellow one on top of the orange. I'm going to pick up the yellow one and put it on the orange. But ignoring that the yellow one is actually underneath the red one. So there again, this spatial arrangement that is not easily addressable by autoregression. Again, GPT-4 is not able to do that. I'm not talking about embodied reasoning, it's even more complicated. Third one is a little more tricky. I got a funny picture, from New Yorker, and what's wrong with this? So we all know basically what's wrong with this. Right? As a human being, we can do very, very good reasoning about that. And then you can see, GPT-4V, the visual version of GPT-4, and look at their answer. Right? So, basically, the reasoning by GPT is to really, equate the human with the robots. They are equally challenged, and they run into the same problems. Obviously, that's not the case, right? The GPT, the machine didn't actually understand. He thought that the human is trying to make the paper balls, and he is helping to make more paper balls, which is obviously not the right. So these are just a few examples about its GPT's limitation in social reasoning, in embodied reasoning, and even in linguistic reasoning. And at the core of this limitation is because the space of action, of activity, and reasoning of LM is language reasoning. It's actually in here. Everything written in language, describable language, is home court, for LM. But what about this one? We have a wider space that we live in, right? Spatial time, multi-agency, the law of nature. All these, only some of that, is falling into a description of by language. Others just exist, but not necessarily, captured by language yet, right? So this complex form of reasoning is beyond what a language model can handle. For example, language model is not very good at describing everything. We all know how to pour a glass of water. And when we pour a glass of water, we don't use the language to reason that. Also, we don't use the law of fluid dynamics to calculate the trajectory. We just know how to pour it, right? And we don't even know how to describe it. And you can ask a language model to tell you how to pour a glass of water. I don't know where they get started with. Traffic, driving, same thing. When you drive, you see a horrible thing like this, many, many cars. Do you actually ever bother to describe them with an article and start to do lingual reasoning? You don't, right? Therefore, LM is useless in here because it will be writing you a long article about every car's color condition and so forth, which is not what you need in editing. And also, even sometimes you could put things into text. It is not necessarily the best thing, and it doesn't contain everything. Okay, we all see, maybe manuals and coach books about swimming, but we all know that you're swimming only by jumping into the water and swim. You cannot read a book and learn how to swim. So similar thing, you hear a lot of other activities, which is beyond what the language can describe. How about the video? Let's say, no, maybe language is too limited. Let's do video, add more information. Okay, so here, another example. I want you to spare a minute to watch. This is a video information meant for human. You can see what you get out of it. So this is a movie shot in the 1940s by psychologists. And it uses basically a few geometric shapes and some motion. So what do you get out of it watching this? It's visual, right? Can anybody just give me just a few words about what you see?
The big triangle is a pulley that's chasing the other two smaller ships.
Wow. So he makes a story out of it already, bully, and then pair of friends and so forth. And that's what we see. No, it's triangle, it's balls, right? Yeah, indeed, you can see many things, strengths and weakness and relationships And even moral judgments, good guy, you probably all believe that it's a big triangle is a bad guy, right? And so on and so forth. I bet if you put this into a computer vision program, any computer vision program right now, what you get is this shape, size, velocity, location, and all that. That's it. Therefore, okay, you have language, now you have a video, you still don't have that kind of human reasoning. What's missing? So I think, here is where I think the next move will be happening, right? We should now go pursue some new models. One of these new models is called the word model. So the word model is very different from a language model. It is meant to be a model that is to simulate possibilities. And here are just a partial list of these possibilities. For example, physical mechanics of real world, embodied experiences, emotional experiences, and social experiences, all that. And we will have a thing to simulate all this, and we call that thing a word model. Can this model be learned? Well, possible. Okay. Basically, this machine need to make use of sensory input of all forms and build a certain machinery such as associative memories, long-term memories, and so forth. But most importantly, it should have a goal, in the training. So every kind of episode of activities come with a goal, come with a perception, then come with a belief. All this basically, gives you more space of accommodating emotions and other human activities. And if you imagine you have this model, then you can do a different form of reasoning. So in the LM, the form of reasoning we do is network prediction. Okay, and it's mechanically, that's exactly what's happening. You do network prediction. And all the seemingly logical behavior is a side product coming out of this computation. It's not by design. Right? So in here, by design, you can do a new form of reasoning called simulational reasoning. In fact, simulation is very, very, very key. It's not a word invented by me or my colleagues. There's a book even talking about the hypothetical thinking. And in our daily jargon, we do thought experiments. All these basically are the same thing. You do thought experiments. You imagine something will happen. For example, when you play chess, when you play Go, do you do massive optimization calculation in your brain? Well, Thomas, you know very well, right?
I try to.
You try to, but it's not working, I guess. You have to simulate. Like the AlphaGo is a simulated machine. You basically do multiple trajectories, then A-star search, and the best one, and execute. But you can imagine doing this for all things. So that requires a very different model, which is not the next word prediction, but the next WORLD prediction, given the previous word and also the actions. Imagine that you have such a model, then what happens to this machine is that given a goal, okay, toward a task, I can basically now simulate multiple plans. And the number of simulation depends on the resource. I can be frugal, I can be also very, very open. And then I'm going to now search for the best thing. Okay, that's what we call simulational reasoning. It is not exhaustive by proof, but it is practically very, very elastic. It gives you the best flexible trade-off between resource and outcomes. And the AlphaGo is actually one of these examples. But you can extrapolate the goal board strategy or configuration to something a lot more interesting, such as in driving. How do you drive? You can kind of imagine simulationally, if I turn wheel this way, that way, what will happen without actually turning it. And then, decide what's go next. Battlefield is a particular thing because fighting a battle is expensive. You don't want to go there and fight, before you have multiple drills and simulations, right? And in fact, even our universe, ourself is the product of such simulation experiment. Evolution happens exactly in a simulational reasoning way. We try many locations, just occur naturally. It's not by design. It's just happening. And then the fitted one survived, others died. And then that's where we are right now. So it's just slower. But imagine the evolution by mutation happening in a computer. That's basically what a word model could support. So that, I think, is an interesting direction was pursuing. And it also offers some convenience for those people who want to understand the world. because what does it mean by understand? It's actually also a very subjective thing. People understand things differently. But with a word model that can simulate, you can actually offer an operational definition of understand. Because if you inject into the word your own action, and you see an outcome based on your own kind of understanding, that means you understand it. You do it consciously, right? And here I give you an example about what I mean. So this is a model that we recently built based on the ideas I just mentioned earlier. It's just some stupid simulations, nothing fancy, not as pretty as a Sora, but you can see that I can actually steer like a simulation. I can say action 1, action 2, what happened, and the movie will be augmented on the fly, go this way now. Well, when you augment and steer, you actually means that you understand objects because you know augment this part but not that part. And if you look at the Sora movies, it's requiring one prompt from the middle, or from the beginning, and then everything is decided by the generator itself. You cannot steer it. And that's actually a high level of pixel manipulation, but not understanding objects. You can simulate also alternative facts or alternative words by different options, and then you can accordingly plan the next move. So in this type of model, what is needed is a representation of the internal states of the word, and then an action that can be entered to change the word. Okay, and then you can carry out a lot of interesting things such as counterfactual inferences, because you can simulate hypothetical truths, okay, and situations, and then among them pick the one that fits your needs and so forth. So it's a very, very mechanical but effective way of making your reasoning and understanding computationally infinite. Again, whether it is intelligence or not, that's irrelevant. I don't care. Okay, so given that, let's see how such a model can be built. First of all, it is a multimodality word. Therefore, you need to have the environment being the source of information. By the way, those environments not only contain objects, but also agents, which I'm going to talk about in a second. And then this information needs to be perceived. And then in this model, you need to have a hierarchical latent space, to keep all this information, represent them at different levels in an organized way. And then, you can call them a thought space where, simulation, or next token prediction can happen, but at a conceptual level. And then you can, generate an action depending on, your thinking process. And then hopefully the environment received your action and had a response, you iterate. Okay, that's the architecture of such a model. Of course, there are a lot of design concerns, down to the details. Here is a whole list that we've been working on, co-embedding of different modalities, cross-modality attention, latent representation, regularization, and so forth. I have no time to go through details, but here is just a diagram so that you know the major ideas, and also this nature of inheriting some of the existing strong results. For example, there is a backbone model which contains a descriptive word that you can do reasoning. Well, before we have anything better, I think a language model makes a perfect candidate, because language model is actually a latent space of the word model, believe it or not. We look at all the words and we turn some of them into our human vocabulary and develop a language for that. In a sense, that's latent space for the word, and we use that. Okay, so the language model becomes the latent space of our word model. But then on top of that, you can form another latent space to implicitly simulate the word with vector or tensor representations. And here you can also incorporate long-term dependencies to make sure that the story goes continuously. And there are plenty of techniques, flash attention, page attention, and all that, reducing the complexity. And then on top of that, you use now a diffusion model, which can generate image and the video based on those visual representations. So many models who are called word models have been focusing on this part, the video generation part. But to be honest, pretty video isn't an indicator of a good inference. It's just a visual kind of impression, good for marketing, right? In a sense, that's the freedom of academic. We don't have to show a beautiful video to the general public or to the big boss. We can focus on this part. You can see the videos that I just showed are not very pretty, but their reasoning power actually is way more powerful than many of the existing, bigger models out there. And then, you can train such a model with multiple experiences, not just the next token prediction, but the reinforced learning, reward experiences, and contrastive scoring, and many other things. We've got a paper in the past talking about how to incorporate such multiple scores in one training framework. And here's a cool, relaxed moment to see the outcome. Look at this cat. Its ear is moving, turn the head in a second, and some cherry blossom fall down. Remember, this is controlled by a command. You steer it, okay? And then you can generate basically arbitrarily long videos if you want to carry through without losing the focus. And that's also why the current video generating models cannot go very long, because if you start from one prompt, sooner or later, after a minute or so, they will diffuse to some whatever places. Okay. All right, very quickly, why we do a word model? Because we need to have agents living in the word model do useful things. Right? So here are the array of things that you can imagine an agent do, booking your travel, writing program for you and so forth. Interestingly, even though we have many companies and teams claiming to be doing agent models, those bigger players are not showing very strongly in agent functionalities. And here are some examples. For example, GPT-4 cannot click the websites for you. Right? They can probably propose you a plan like this, and I want to do ski travel, and they will give you some flight plans, but they cannot book for you. You need to make that booking. So actionality is a problem. But that's not the biggest problem. You can, I think, make a long chain type of arrangement and put other agents to click for you, but that's not the point. When to click and also what context to act is the bigger problem involved. Here is one example. Now I asked all these snow and ski plans and so forth, you got a plan. And now you say, hey, I want to go ski now. How about you book one for me? And then what he will say, oh yeah, these are the flights and go to us and so forth. But he didn't remember that the time I was typing this query was in July or in June. The context was wrong. Asking at that time was not snowy yet. So the agent model, need to have that kind of a word model inside to know the bigger context in every activity. And that is not what the current language model is built upon. And therefore, here is an alternative design of the agent. Right? You actually have a word model as a module inside, the agent's brain. Then you have alternative representations of the belief and the goal, and then the plan accordingly, from the goal and the belief. And of course, the external augmentations, to be verifying, or suggesting the beliefs. And here is just a instantiation, in the traffic, in the driving stuff. Your external message become this, and then your reasoning and planning will become your driving behaviors and so forth. How to implement that model? Again, we've been trying a lazy idea. We try to use as much building block as possible out there, and to really turn the bigger system into components, each of which can be utilizing a language model. For example, this is a word model where we need to generate the next word. How to represent the next word? Maybe a bag of words, maybe an article would be fine. Because if the word is written as an article, then a language model can be directly plugged in and do the inference. Plan. a policy, what is a policy? Well, how about we just turn the policy into also a little blurb of writing, and then the LM can be also used for that. So it's not good, for example, it's not going to work for swimming, but for booking tickets, things like that, it should work very well. Right? So our current design is to make use of the language model here and there in very different places, generating action, generating next states, and do state transitions and so forth, all using different specialized language models. And then we can augment that with video and other informations. And then, using this analogy, you can imagine, going flexible with resolution, and you can coarsify the model to define populations of agents, because that's really what a real world like in this room is about. We have maybe 50 agents sitting here. You cannot treat them as objects. They each have their own movements and minds, right? And then the agents can be turned into a super agent and dealing with collective behavior. For example, I'm the FCC, the boss, who need to make an economy or a banking policy. I'm dealing with a population of agents, who react to my policy in different ways. And therefore, you don't have to look at every agent. You look at them as a whole. So in econometrics and in social science, these kind of in and out resolution is often needed to study different behaviors. I think the agent model can be there to be a building block. So here I gave you a video demo, last one, to give you a sense about how an agent model, would simulate the world, compared to say a Sora model, a video kind of general model. Again, the video quality is not pretty, but you can see some differences. Sorry. It's a little bit subtle, so I will encourage you to watch more kind of closely. It's not like that beautiful lady walking in the Tokyo street, so elegant, but he has something different in his mind. See, he's interacting with other people. And he is also standing in front of certain cars, but not other cars. Okay. And then he does some other strange things. Why? There's a difference here. When you have a standard video model, the cars, the people, and all the other things appeared in that video, except you, are objects. They are literally lifeless objects. And all your goal is to avoid them, bump into them. You don't interact with them. Imagine that a car is driven by a person who wants to kill you, or who wants to chase you. What you will do? You no longer treat that as an object. Okay, you treat that as a predator, or a friend, and that's the agent-agent relationship. It's not through objects. So in this video, even though it's not of a high, pixel quality, there is this interaction and engagement between the agents. Everyone in here is actually an agent model with their own world. I can actually turn myself into the other people's eye and see this guy running. I will see a different thing, and I will have a different judgment. So that's actually the difference of what the current model is not able to offer. Just to sum up, here, the external environment has other agents, and these other agents live in a broader world of reasoning space, not just language, but also all these other things. And then they need to create correct signals to be represented, in this thought space, and then going back. So, here, there are new capabilities required, such as hypothetical thinking versus inductive thinking. And you can ask interesting questions like the completeness and soundness of this representation, and how to design the building blocks. Should we use ALM, or in the future we have new architectures like mixed experts, which can be incrementally trained and assembled, and of course a lot of engineering issues. Okay, so with that, I think I'm done with today's job. This one is just a precursor of yet another reasoning space in the biological world, which is actually equally, if not more fascinating. Again, here, as long as we give up the goal of become a biologist, try to explain biology, But to focus on simulating biology, I think this goal is also achievable because biology is so complicated. I don't want to really go through. Our goal is to, again, build this multi-scale, biological model. Multi-scale means that all the way down from molecule to a organism with one model built on all this data and solving all these different tasks. And on next Monday, I'm going to talk about a project in that space. So with that, I'm ready to wrap up. Just to sum up, here are the high points in my talk. I think it's for academic in particular, it's probably productive to focus on functionality and utility instead of the hypothetical philosophical term of intelligence to orient our projects. And I argue that LM is a simulator of lingual, therefore other models could simulate higher level entities and phenomena with models beyond LM, such as in physical and biological and the social world. And we've been working on this list of projects. Today, I talked about the LM360 and also this what I call the PAM model for the word models. And next week, I'm going to talk about the idle models. Okay, so here are my philosophical slides, which I don't have time to go over. In case you are interested, we can just use the open QA time to have fun with that. Yeah, the point is that you don't have to go through this human evolution from experience to knowledge, writing a book, writing a paper, and then to a solution. You probably can go directly from experience to solution with a black box model like we did in LM. That's equally plausible, if your focus is on functionality, not others. All right, with that, I'm done with my part. Thank you for the attention.
Thank you, Eric, for the wonderful talk. I think that should really be a 3-hour talk for 3 talks, not just one talk.
Well, it's a collection of 4 years of absence here, so I thought I should be fair to all of you and talk present enough materials.
We should have a talk for every day for the whole week. But anyway, we are opening the floor for the
yeah, thanks for every talk. I really enjoyed it. And especially I like your position for treating this kind of large model as various simulators. But on the other hand, I think even though we don't call it like intelligence or something like that, but on the other hand, we still need some metrics to track the progress in this model. And for example, we use kind of like the university's student example to see, like what is the people listening for our model. But I also quickly tried like example using O1 preview just now, and it can actually solve the problem very well. This like can say, there's something wrong with fundamental with your fundamental design of this algorithm, something like that. So in that regard, that means we still need kind of metrics to track this kind of performance of these models. So in your opinion, do you think using what kind of metric on what kind of data sets you think the models will reach maybe so-called intention, or maybe just meet your own expectation? Yeah, that's my point.
In LM, the metric has been
Can you repeat the question?
the core, if I get correctly, is that what metric we use, to evaluate all these advanced models, right? Again, in LM, I think the metric has been well established. And in fact, the truth is that the LM is beating human in every aspect, all these standard tests and the Olympic math and so forth. In word model, there hasn't really been a agreed upon, standard benchmarks yet, right? But I think it's getting there. The reason why there isn't a text is because whether it's too simple, like object recognition, that's not really meant for word model. But for higher reasoning tasks, people confuse from intelligence versus functionality. So I can, for example, get a couple of tasks in the nature of counterfactual inference, or occlusions and so forth. I ask you to go and I put something behind the building and which never appeared in your visual thing. And then, after you do a bunch of random things, you go back to the building on the other side, you see, what do you see? That kind of thing isn't in a task yet, because that's not in the vocabulary of the current people's definition of intelligence. Right? So I think it's a field that is to be defined. You guys should come up with your own tasks and benchmarks. Right? In biology, which I didn't have time to talk today, better. Okay, in fact, the model and the benchmark we're going to release next week has 300 plus different downstream tasks, which are very factual. Biology has the benefit that it is not very subjective, because it's not meant for human to consume, right? A knockout is a knockout. A structure is a structure. There is no other configuration, ambiguity, and so forth. And in human being, we talk about alignments, we talk about safety, we talk about fairness. All these definitions, in fact, in my opinion, is not a benchmark, because safety here may be different from in Europe, from the Middle East. All these are very subjective. Right, so that actually hurts AI. With all these different, slightly more kind of consumer-oriented and politically oriented evaluations. It's not helpful for the AI science itself. It's helpful for product, right? And again, AI has now this ambiguity. What is a product? What is the methodology? Here, I want to make a disclaimer. I'm focusing on methodology. Okay, I'm not just thinking about how to make money out of it yet. Someone should figure out for that.
I have a question. So you mentioned using the LLM as the world model, sort of like the backbone for that. I think that makes a lot of sense. And personally, like, I kind of have a monologue going in my head most of the time, but even then there are some experiences that I can't describe in words. And I'm wondering what you think. Where do you think we'll go in terms of being able to have role models that can do like embodied tasks and have that physical understanding?
Yeah.
What thought I have is like getting for the big companies to train something like an LLM, like a transformer with multimodal like embodied data, but it might take some time, I think, for me to collect all of that and train it. So what do you think we should do instead?
So you here already have some kind of hint about what's going next.
The people on Zoom as well.
On Zoom as well. Okay. They cannot hear me?
No, the question.
Oh, the question. Yeah. The question was in the more complicated case where inside a word model, a language model is insufficient to carry out some of the reasoning. What should we do? Something like that, right? Yeah. So I think my answer is that this is just an option, but not the kind of choice, right? For things that can fall down into the word space, we do it because it's already ready-made. But I also have, for example, directly visual tokenizers, and you can also use prompting and supervised learning in the video space based on tokenizer directly, to train motions and activities in that word. So what I'm trying to say here is that it is a framework that can be pluggable with different architecture components, right? And then, the way you train this model based on our experience is always not about throwing everything at the same time and train a big mass of everything. You usually can do it in a modular way. You started from here, you add them to that, because some of the content in the video tokenizer tokens can be actually aligned with some of the word tokens. And that alignment allows anchorage. And then you extrapolate into the ones that is not aligned. So there is an incremental way of doing that. But in terms of whether we wait for big companies to do it, I'm not sure. I think you need to wait for very long before you know what they are doing and what's working and what's not working. I would say academic should at least get involved in such businesses, and also maybe change a mindset. Some of the mindset is not about not having machines. If you feel like you have to publish a paper in 3 months, you cannot do it, right? If you are willing to invest, a year or two with a team of 10 students, you actually can do a lot. Okay, our K2 model, was trained on very, very small number of GPUs. Okay, only a few hundreds, about less than a tenth of what Meta used. But over 9 months with tens of students, very, very hard working on that, and we got it. Right. So there is a different mindset that is not very, very popular and mainstream among the academia. But for those who are willing to give it a try, you have opportunity. Yeah.
Maybe,
I have multiple, but I can ask just one of them and ask something later. So regarding the K2 and creating the models in the academia, as you rightly mentioned right now, there is two ways that we can approach this. One way is, I feel it's one is the data. If you have better data, maybe you can challenge the scaling laws. With better data, with less compute and less GPU, maybe you can achieve the same performance. Second thing is just directly challenging the existing models, such as, is attention really the right way to go for scaling up, or is there something which we are still missing from, let's say, MLBs or CNN, some inductive biases that we can bring in? So I'd like to know your opinion on exploring these two paradigms for challenging these big models, because that's where the innovation could come in.
The question was challenge the status quo with two proposals. One is to work on data, better data, and so forth to overcome scaling law. The other is to challenge the existing architecture, like the attentions and so forth. Yeah, I have a very, very unconventional, strange opinions on both. Sorry. Data. I don't think, again, I'm in a position to believe that there are no bad data. Every data is good data. Every data is a fact. Even if it is wrong, it says something about the world. You have to take it. Right? It gives you a true reflection of the complexity of the world. Therefore, I only reject data who are of a wrong format, or not storable, or somehow very, very, badly kind of maintained, something like that. But content-wise, I don't make any judgment, because in fact, in biology particularly, there are always this argument about noisy data, unnormalized data, and all that kind of thing. Well, human error is part of the world you have to live with. Your model need to capture that, rather than I pre-process data, remove all that. It's like growing a child. You put them into a conservatory with no germ, nothing, and very clean. That person will be very unhealthy. If you expose that to everything, it's the natural way. So I wouldn't be so picky on data. That's my position on the first one. But I need to actually work more on the architecture part. That I agree. There has to be a lot of room for architectural innovation. But even the existing architecture actually still are far from being well utilized. I give you one example. I raised this to many of my group members already. We human brain and the human eye process information not in the form of a transformer. Okay, when I look at you, my eyes zoom on you. Everything else, all other pixels are blurred already. It's not getting my full attention. Therefore, my transformer, in my brain is not uniformly applied. This pairwise attention is not uniformly applied to everything. Therefore, it's very, very economical to focus on this, right? My sight vision and my focal vision are different. And the language, same thing. I can imagine that I don't do that kind of 1 million, token long context in my reasoning. I have ways of abstracting them. I can abstract a whole book, in my prior when I do the next thing, rather than using a full attention of 1 million tokens. Right. So all these, very smart idea in a biological brain are not even utilized yet. So there's a lot of room, even in the attention model space in transformer, you can do better. Then, of course, there are phenomena that is not attention. For example, in biology model, we are trying something called the higher dimensional positional encoding, where your encoding is not just a linear sequence encoding. You have a lot of positions depending on what function you are performing and all that, right? And whether you still have that kind of cross-product attention, again, questionable. Right. So yeah, I think depending on your problem and your data modality, we are literally at the beginning, of doing this computation. Algorithm is another issue. It does bring to gradient learning or just a one-shot learning. I don't, it's all different. It's all open at this point.
Yeah, I really like that UE5 example because nowadays gaming industry, they are developing great engines for simulating. So probably a crazy idea is can map the physical world into the UE5 objects and trying to just simulate that into the UE5 and train a model on that with them. Because we human we train ourselves based on perceptions, but in the engines we can have all of it.
Yeah, agreed. Yeah. Although in the game industry, the way they simulate the world, which appear to be simulating, is based on predefined rules, right? So that's actually a difficulty for people who work on world model to make a convincing case, because usually their simulators are not even as good as the game simulator, even though they use a different mechanism. And that's something I usually remind my colleagues not to simulate a game at this point, because games are too advanced. It's an industry with millions of people who write all the rules already. You don't have advantage. You want to be in a space where, it's a Wild West. Not too much has been done yet. Then you're more kind of, how should I say, the intrinsic world model can make a difference, hopefully.
Yeah, I'm very interested in the idea of language as the latent space of the reasoning and planning. But I'm thinking that different from the latent space of neural network, the language may be vague. So how do you think about the ambiguity of language? Do you think a program may be a better communication method here?
Possible, yeah. Language is vague for, I would say, for good reasons. It is a product of evolution. Okay, it's vague for a reason because there are subtle differences, right? And even when we use synonyms, we actually mean subtly different sentiments and maybe even different context informations. So I would leave it that because there is a huge benefit for using that. Language models are so well trained already. We already see a proven point of being very successful in linguistic reasoning. And before anything better can replace that, I would stick to that for a pragmatic reason, right? If I do coding-based, very, very strict kind of artificial language, I know there are artificial languages which are very, very rigorous and so forth. There are not enough training data and not enough, kind of successful use cases for that. So yeah, I think it's cleaner in theory, but in practice, it might not be working as well. That's my hunch.
Well, we have 1 minute. I want to have a few rapid fire questions. No think, just a rapid answer. One model or many models?
One model or many models for what?
Do I need one foundation model or many foundation models?
Oh, it depends on how you call it, right?
Rapid one answer. Choice.
If I use 2 words, one system.
Okay.
Yeah.
Big model or small model?
Big model.
Graphical model or deep neural network?
They are the same, right?
Vision or language?
Both.
Okay. Copilot or fully autonomous AI?
That's where I love to have some conversation. In fact, I meant to have a philosophical conversation. People are talking about autonomous AI being scary and so forth. People are talking about agent models being scary and so forth. Do you know what is agent and what is agency? What makes things scary is the agency. It's not the agent. Okay, I think people don't even know what they're talking about when they are scared about something. They are scared about A, but we are building B actually. We're not building the thing they're scared about.
Okay.
Autonomous AI, just like autonomous car and so forth. Are they scary? Not really, right?
Okay.
Your washing machine at home also is autonomous, automatic.
You want to fully autonomous?
Yes.
Okay.
When I need them to be autonomous, I want them to be fully autonomous. Yes.
Good. physics or statistics?
Is that a binary?
Okay, you have to choose one.
Of course, physics.
Oh, okay.
Yeah.
Elon Musk or Sam Altman?
Or Elon Musk, someone both. I mean, I think to me, they're the same person.
Okay, great. That's wonderful talk.
Yeah.
And let's thank again Eric again.
So wonderful to be back. And I love to talk more in the future about this.
And also, Eric mentioned to me that his care. So if you want to talk more about this topic or other topics, feel free to reach out to him. Yeah, thank you again.
Thank you.